Hey everyone, welcome to the Convo AI World podcast. In this podcast, we interview builders, developers, and teams that are building solutions for the conversational voice AI space. Today, I'm joined by Ziyi Lin, a speech engineer from the 10 team. Welcome. Thanks for joining me.
Yeah, thanks for having me. I'm glad to be here. Thank you.
Everyone's familiar with 10. We met with Ben Weeks in our first episode, but for those that are not familiar, 10 stands for the Transformative Extension Network. It is a framework for building multimodal voice, video-based AI agents. And today we have one of the core engineers from the team who is focused on speech. So I'm really excited for this one. And let's dive right in. So, Z, what problem was really the catalyst? Like what was the reason that the team decided to create this open source VAD rather than continuing to use an off-the-shelf solution?
Yeah, this question is quite good. We all know now is the AI agent, or let's say conversational AI era. So with the rise of AI agent, the VAD, the voice activity detection, has become even more crucial. It's become more and more important nowadays. So we need systems that can quickly spot the SOS, the start of sentence and end of sentence, in short, EOS, with lower computational load and smaller library size. Also, the VAD system has to handle false negatives and false positives well. So in other words, the VAD system should have high performance and should really be agent friendly. And in addition, it should be able to detect the short non-speech segments between the two separate sentences in order to lower the end-to-end latency. And existing VAD solutions just aren't cutting it in some aspects. So I will take the old school VAD system as example, the traditional energy-based VAD or the pitch-based or GMM-based VAD from WebRTC. They are not robust against noise, thus resulting in high false alarm rate. So we cannot use it in the voice AI agent. And the SOTA deep neural network-based VAD called Zero VAD has high latency. Well, the latency may not be tolerable. So this is why we decided to develop our own open source VAD systems.
Makes sense. It sounds like there were a lot of really strict requirements. You said, from start of sentence, end of sentence. Those sort of things are so critical, I've come to notice. Like the more I play with conversational AI agents, it becomes apparent that sometimes if you don't have a really good VAD for it to detect that like end of sentence, it kills it. Like you're sitting there going, "Did you hear me?" It's like the old Verizon commercials, right?
Okay. Now, for example, if the end of sentence cannot be detected quickly, then the users like you are using the AI agent, are always waiting the agent to give you an answer, give you a response. But after 1 second or 2 seconds, you didn't hear any response from the AI agent, you will be angry and say something continuously or after. Then the experience is not
do
good.
that. Huh? Yeah, the experience is not as good. You're right. All right. The off-the-shelf stuff was not cutting it. And the idea is like, all right, we're going to make our own. All right. So walk me through this. Like, was there a pitch or a prototype or what kind of convinced the team to be like, yeah, we're going to go this way. We're going to do it ourselves.
This is very easy, very simple. Just because our VD has better performance comparing to the SOTA one, the SOTA deep neural network base called the Zero VAD. Yeah, and we have better performance. We have lower false positive rates. We have lower misdetection rate. And also we have smaller library size. Our library size is just several hundred kilobytes in size. And on Linux, our library size is just about 300 kilobytes, but for Zero VAD, it is about 1,000 kilobytes or 2,000 kilobytes. Yeah, and in addition to that, we also have lower latency. We have tested the latency of serial VAD. It is about also several milliseconds, and we only have dozens of milliseconds latency or 100 milliseconds latency. So we can have better user agent interaction experience than serial VAD. So we have higher performance, we have lower latency, and we have lower library size in summary.
No, that totally makes sense. And I think it's that super compactness that really makes it appealing, right? It's really lightweight. You're talking about at least, or at smallest, a third, like, right, if you're using a 1,000 kilobyte versus like 300 kilobyte. And then if you have a 2,000 kilobyte, you're talking about like a sixth of the size. That's orders of magnitude smaller. And you're saying it responds faster. It can detect better than the zero VAD, which is kind of like the standard, right? That's what most people are using now. So looking back at the setup and when you're planning the development of this, what early design choices did you make that really made that big difference in hitting the low latency targets while still being able to have like the model size?
First of all, let's talk about data. Let's talk about the training data. We actually use precisely manually labeled data for training other than the open source data, because the open source data provides our label, but the label is in a low precision. So we cannot use this data for our model training because the precision is so low. The label is not correct. I mean, the cheapest is the most expensive. If we just use the open source data for training, then our VAD model will learn the latency just from the low quality label. And therefore, the experience would be worse due to high latency. So from here, we can see that VAD plays an extremely important role in human agent interaction. And secondly, we use a physical feature. We call it pitch. The pitch is a very important characteristics of our vocal cords. We use the pitch, or let's say the fundamental frequency, in the input feature. This is the second point.
So the first real differentiator was the data. Like that, it all comes down to that core training data, right? Like the better the training data, the better the
Yeah,
result.
because this is a data-driven approach. I mean, the deep neural network, deep learning era, right?
So you had high precision, really well labeled data that was something that you could train on. And you're saying by adding in the pitch, you're able to like differentiate better as to what is start of sentence, end of sentence. Like, how does the pitch play into this? Can you maybe unwrap that a little bit?
Because pitch is an important characteristics of our vocal cords. Only when our vocal cords vibrates, it will generate pitch or fundamental frequency, noise, or
No, I totally understand what you're talking about, like that pitch. But when you're talking about in the sense of the activity detection, right? Like how does pitch or like the pitch data play into that detection? Like can you kind of walk us through the understanding of it?
because only human voice, human speech contains pitch, but noise not, and the model can learn these characteristics if the models see the pitch is less, for example, 100 hertz, then the model will think maybe someone is speaking. If the pitch is 0, then there should be no one speaking. There should be noise or
Gotcha.
other
So that's
voice.
like a way of detecting the background versus actually like what the person is saying from a model's perspective, right? Like, because the background noise, something that is not a voice will have a constant pitch or no pitch at
Yeah,
all. Sorry, no pitch at all. And then if there is pitch, this is voice. So that's
yeah.
like one of those differentiating characters in the sound space. Okay.
So pitch is very important in the whole model design.
That's very interesting. I had no idea. When we're talking about pitch is perfect for this because we'll lead into really what kind of algorithms or signal processing tricks allow this VAD to really be really robust across all the different diverse inputs, right? Like microphones, environments. Is it just the pitch and the training data, or is there something even cooler about this that we can dive into?
First of all, the training data, we collect the training data in many scenarios, in many rooms, room configurations, also with many different kinds of microphones, many different distance between the speaker and microphone, and different reverberation. Also, the pitch feature you mentioned, but last, we use Multitask to train the model. So our VAD model not only do the voice activity detection task, but also do another tasks. And these tasks will help the VAD task to learn better and to help the model to better detect speech and noise.
So it's almost like the algorithm is self-learning as it's going. So like even as it's working, it's improving its understanding of the voice versus noise ratio. And it's interesting, you say like you tested on different input, or you trained from different inputs, different environments. It feels like the scale of the training data is probably bigger than the scale of training data most other companies have access to. So when we talk about VAD doesn't really operate in a vacuum. It's the critical first piece in Ten's cascading model, right? Like
Yeah.
the VAD is what like triggers the downstream LLM and the TTS modules. And how do you manage that state in real time for the VAD to be so precise in that?
Yeah, VAD essentially acts as the traffic controller here by detecting both the start of sentence SOS and end of sentence EOS, as I mentioned before. It is what triggers the entire chain in the real time. So, for example, once VAD picks up the end of sentence, like 200 milliseconds silence, well, this time we can adjust based on our needs, and it signals the STT system, so the speech to text system, to finalize the transcription. And this transcription will then be sent to the LLM. And the LLM outputs and then triggers TTS to synthesize a response. So this is why low VAD's latency is very important in the conversational AI application.
Yeah, it's like that first, like you said it best. I've never heard it said that way, but I really like how you put it. It's the traffic controller. It's
Traffic
like,
controller.
let's go. You're coming in. We're done. That's it. Time to process, right? End of sentence and end of speech. Let's get it moving. But another critical point of that traffic controller is also to be like, oh wait, stop this whole process.
Yeah.
We have an interruption. So VAD has to like, the start of sentence, right?
Yeah. Yeah, the start of sentence controls the or affects the interaction latency, I think, and the EOS affects the whole end-to-end or response latency. So it's very important.
Yeah, it's such a critical piece. And then when you see 10 being run, right, and this VAD, is it more edge or full cloud? Like how important is it where you run it, and given like dependent on the use case?
The VAD model is essentially is basically very small. It is very small, only several hundreds kilobytes. Typically, it can be run on edge devices to ensure low latency detection of voice activity. Yeah, and users hate delays when interacting with agents. Running VAD on the edge just cuts down the lag because it is right there on the device, detecting speech starts and stops instantly, immediately. And the another thing is about the bandwidth and the cost savings. Yeah, if the VD is on the edge, it only sends audio frames that actually have speech to the STT, speech to text, or at the ASR system, whether that's on the edge too or in the cloud. And it can help you or help the users to save the bandwidth costs, the STT costs, and keep things efficient.
Yeah, that's huge. The STT cost is something you don't want to like mess around with, right? Because that
Because
could
you
be
because you don't want to just send send the noise or send the non-speech segments to the STT systems because it is not meaningful.
Exactly. Yeah, nothing would come out of it. You're just burning tokens. In terms of earlier, you spoke about low latency, false positives, that sort of thing. What kind of benchmarks are we running here to, how do we compare these with the alternatives? And because I know we said it's faster, it's better. How do we know that?
To be honest, there are many open source data sets, but with no precise enough VAD labels. If we just use these data sets for evaluation, it may lead to wrong performance results. In order to address these, we built a very large data set combining our real-world recorded data and the filtered version of open source data. What does it mean, the filtered version? We do manually label the data. We didn't use the original label file of the open source data because it is not precise enough. So by using our precisely manually labeled data, the evaluation is more reliable. So in our large test sets, we have lower false alarm, lower miss rate, and large area under the curve, large area under the precision recall curve, which is a very common metric in the classification problem. Comparing to the SOTA open source VAD, zero VAD, we have better performance. We have lower library
So
size.
when running the open source on our data sets, we could see the performance difference. And then even when labeling the public data sets, we still outperform them.
Yeah, you can just go to our GitHub site and you can see the PR curve of our 10 VAD and also zero VAD and also the pitch VAD from the WebRTC. You can test by yourself and
Perfect.
also with your data. But the point is label. We should do manually precisely label.
That's the big key that's the secret sauce, I guess, right?
Yeah.
And because it's open source, we can kind of share the recipe. The recipe is make it from scratch.
Yeah. As I mentioned before, the cheapest one is the most expensive one.
But it's also the most performant, right?
You should put some efforts on it.
Yeah. I mean, I'm going to take your word for it on this one. When it comes to this accuracy, right? How do you maintain that accuracy when users are switching between like speech, music, maybe there's background noise? So like the person is maybe moving or there's things moving around them that are causing the environment to change.
I mean, these scenarios are all in our training set. To be honest, our training set contains data with switch between speech, music, or background noise during a session. Thus, the model can learn the switch between different scenarios and give the correct voice activity detection. And our training data containing many kinds of scenarios, not only these. Thus, our model can adapt to different use cases, different scenarios.
Nice. Well, that's huge. It all comes right back to that core data set. Like, just not going to escape. Good data, robust data, well-labeled data. If people aren't getting the hint now, data.
As I mentioned before, data-driven approach.
Yeah, it's all about data.
And also the pitch feature, our model design, our loss function design are also critical.
They all roles in supporting in this. Yeah. So this thing's light. It's like 300 kilobytes. So when you're talking about like CPU performance, because the CPU has limited, like the smaller the better, right? Like it's not a GPU, it's not doing parallel processing, you do a lot more serial, maybe you get some threading in there. So when you're talking about running this on like a mobile device, is there going to be a trade-off there with like CPU and detection precision, or is this something that's going to still perform?
Good question. But honestly, we didn't have to make huge trade-off between CPU usage and precision on mobile. And I will explain to you why. VAD is basically a simple binary task, right? It is just the classification of two classes, speech and non-speech. It just needs to tell if there is a speech or not. So that let us keep the model tiny, only a few 100,000 parameters. So even on mobile, it barely uses any CPUs at all. We can always run our VAD on the mobile. and it doesn't affect the CPU performance a lot, just a bit. You can totally ignore it, and basically the task's simplicity let us avoid that tough choice between efficiency and accuracy. It runs just light on mobile, but still catches speech reliably. So in summary, don't worry about the CPU usage since the model itself is simple enough.
That's awesome. So I like how you put it. It's a yes or no question, right? Yes, keep going. No, ignore it. So, and we all know mobile, that's like the ultimate edge. That's the closest you're going to get to the user to being
Yeah.
able to run something right in the user's hand. So that's awesome that it can be deployed on mobile and have virtually no impact on the CPU. Do you guys have feature requests coming in from like the community or not really?
The feature request, I think no feature request from the community right now.
No, yeah, it's pretty new.
Yeah,
Okay,
maybe after several months.
we'll check back in. So we're going to skip down to like the frontier thinking. 10 VAD has kind of like solved this challenge, does it a lot better than really the market alternatives. What are the unsolved technical hurdles here? Like, can we solve overlapping speakers or maybe whispered speech or, multilingual? Is that on the horizon for VAD or does that go somewhere else in the whole AS line?
I think VAD is only responsible to detect whether there is a speech in the audio frame or not. And the VAD itself is multilingual. We can use the VAD in any kind of languages because we are all the same. Our vocal cords are the same.
It's very distinct, right? Like it's human vocal cord sound versus any other animal or any other
Yeah.
sound. Yeah.
Yeah. And also, overlapping speakers seems not a task of VAD. VAD just can detect whether there is a speech, but the VAD will not know if there is two speakers or three speakers or many speakers.
It doesn't really care. It just says this is speech, pass it to the next step, right?
And the whispered or weak speech detection is a big challenge. For example, when someone speaks softly, like whispering, haha, or yes, but the audio signal is extremely low in energy. Yeah, this makes it easy for VAD to mistake it for non-speech and miss it entirely. And with the develop of deep learning, the model itself can learn the characteristic of whisper speech. The model can detect the volume, although the speech is in a low volume, the frequency structure, the spectrum structure is still exists. So the model can extract these features out regardless of the volume.
So it could do that now. The current one does this.
Yep.
Oh, that's
You can
super
try.
cool.
You can try our model, right?
Yeah. Well, no, I've tried it. I think this is more just so for the people listening along to kind of hear this spoken out, right? Seeing is believing, and you bet we're gonna include some links to the Hugging Face, to the benchmarks. We'll make sure that this is all included when we air this live or air the recording of this. So we'll make sure that everyone has access. But for right now, I'm going to pick your brain a little bit more on some fun stuff. So when we're talking multimodal agents and we're adding video, how might the VAD collaborate with like the visual silence detection to improve that turn taking? Will the VAD play a role there, or again, will that be another piece of the puzzle?
I think VAD and visual silence detection can help each other, but they need to work together. For VAD, VAD checks the sound when someone starts or stops speaking, and the visual part, the visual checks what we see, like if their mouth is moving, like when you are speaking, your mouth is moving, then together they are better. Yeah, for example, if VAD hears silence, but the camera sees their mouth is still moving, We know they are not done, and that stops the agent from interrupting. It's too early. Yeah, but there are also problems. Yeah, sometimes someone stops speaking to think, and then VAD will hear silence like this, and their mouth might stay open, and then the visual part cannot tell if they will keep going, or in a noise place, VAD might think a noise is a speech, so the misdetection. But the visual sees their mouth is closed, so that fixes the mistake.
They work together to like correct
Yeah,
the outliners. Yeah.
if one makes a mistake, then the other part will detect better. So we need both. VAD for the sound and visual for the looks. They can help each other, so get it right more often. It is not perfect, but better than just using just one.
No, it totally makes sense. And humans aren't perfect at understanding when people are done speaking either. I've totally been there where you're on a video chat or a video call, and maybe there's a little lag, so the person stops to think. Plus, the connection's a little laggy, and you start to talk, and then it starts to come in. You're like, oh nope, that was not my turn. Right, and that's just human to human. So with AI, it's super cool that there are these efforts to kind of meet the human to human interaction there, right? Like there's always going to be that little bit of mistake, but the closer we can get, the more lifelike and the more we want to
Yeah.
interact, better experience, right?
Yeah. In addition, if we wanted to detect the turn better, maybe we should use some semantic model to detect the semantic information. For example, if you are saying, "Hello, how are you? How is," and then you stop, and then you're thinking, "Oh, what I'm gonna to ask," then you say, "How is it going?" The semantic is finished. So the next speaker can react.
Yeah, no, the
Semantic
semantics are
formation.
huge. Yeah, it plays a huge role into it, right? So we've been having a great conversation here, and I appreciate your time. But we are nearing kind of like the end of our chat, and at the end of all of my conversations on the Convo AI World podcast, I like to ask a little bit of a wild card question. So for you, if you had kind of like a free opportunity to just hack on one Moonshot feature for 10 or 10 VAD, like the speech elements in 10, what would you build? I mean, from like a speech engineering, it doesn't even have to be from a 10 perspective. Like, right, if you as a speech engineer, let's say you're not working on 10, you're not working on anything, you can choose something really cool that you want to focus on. Just what would that be? Like, let's say in another life you weren't working on 10, you're working on whatever you can dream up. What would that be?
I would like to build a model that can detect the emotion of the speaker, that can perfectly detect the emotion of the speaker. Because if you just use the transcribed speech from the STT system, it is just a test. No emotion information at all, and you will never know if the speaker is angry or is happy or is what kind of emotion. So emotion detection is very important in our AI agent. Otherwise, the agent will talk to you just like an agent, not like a human. Yeah, just like a machine.
Yeah, I think that's actually like a really interesting point you bring up, that emotional context, that emotional awareness. And I think I've maybe seen one or two demos where they get that right, and it's uncanny, right? They understand and they inject the emotion back into the AI, and it has like the awkward ums and it feels human. And I don't know how to
Yeah,
explain it, but like that emotional connection takes it to another level.
Yeah, you're right.
Yeah, it changes the interaction completely.
Because now the AI agent is just talking to you, but it is difficult to understand your emotion and gives you the appropriate response to you. Because if you are sad, the AI agent should should feel your sad, how to say, sad emotion, and
Yeah,
try to
it should
say
be able to
something
empathize, right?
and should be able to say something to let you calm down. Yeah,
Yeah, and now there's in the TTS I've seen you can inject like
yeah.
emotional stylings, so that becomes even more important, right? So understanding my emotion to be able to continue that chain with their emotion or their
Yeah,
perceived.
but there is also many problems with the TTS system, because if we use the large language model or large model in TTS system, the system will behave non-stable, not very stable.
What do you mean by that?
The TTS system will say something that you don't expect. For example, if you want the TTS system say hello, how are you today, and then the TTS system will respond to you, what the so LLM is not very stable. I just want to point it out. This
No, that makes sense. I
or
love
use
that example.
another emotion, or just speaks in a very strange sound. The pitch is very high. The normal people pitch is about 100 to 200 hertz. The TTS, maybe the speech generated by the TTS system has speech about 300 or 500 hertz, and it will sound very unnatural and very strange.
Not true. No, that makes sense. It's that little difference is that nuance is something that we can pick up on, and it's what really differentiates between something that sounds realistic and something that sounds like rude and weird. And it's funny because over the years, and by years I mean hundreds of years, that humans have evolved between their senses, right? Like eyes, sound, sight, hearing, and the ability to differentiate between what is another human's voice, what is a sound in your surrounding, what is a normal voice, right? Like what is an actual person versus a machine. We've become very sensitive to that. Having the systems and the agents that can really do that right and execute correctly is important, because it otherwise falls into this part where it just leads to a terrible user experience. Well, Z, it's such an amazing conversation. I really appreciate your time on this. I'm so excited for all the new stuff coming out with 10. But like, for anyone that hasn't tried the VAD, the open source, we're gonna have the link to the Hugging Face. And I really enjoyed this conversation. I learned so much today. I'm not gonna lie. I thought I was decently versed in some of this, and I learned I have like so much more to go. But I appreciate you peeling back like those top layers and giving us a lot of that insight into what drives a great VAD model. Thanks.
Thank you for having me.